Welcome! In this session, we'll tackle LeetCode problem number 395, longest substring with at least k repeating characters. This is a fascinating string manipulation challenge that tests your understanding of substrings and frequency analysis. Let's dive in and explore the problem in detail. In this problem, we are tasked with finding the length of the longest substring of a given string S where every character in that substring appears at least k times. If no such substring exists, we simply return 0. The input consists of a string S made up of lowercase English letters and an integer k. The output is a single integer that represents the length of the longest valid substring meeting this condition. This means we are looking for a substring where the frequency of each character is not just equal to, but greater than or equal to the value of k. Let's go through the first example to understand this better. Here, the input string is s equals ob and the value of k is 3. In this case, the output is 3. Why? Because the longest valid substring is AAA, where the only character appears exactly 3 times. This satisfies the condition that each character in the substring occurs at least k times. Now, consider the next example with an input of s equals abab and k equals 2. For the second example, the output is 5 because the longest valid substring here is abab. When you examine this substring, you'll notice that the character A appears twice and the character B appears 3 times. Both of these frequencies meet the requirement that each character must appear at least k equals 2 times. This makes abab the longest qualifying substring. Now, let's analyze a third example where s equals abcd and k equals 2. In the third example, the output is 0. This is because no substring in s equals abcd meets the condition. Each character in the string appears only once, which is less than the required frequency of k equals 2. Since there are no valid substrings, the result is 0. Finally, note the constraints and edge cases for this problem. For example, if k is greater than the length of the string, the output will always be 0 since no substring can meet the condition. Similarly, when k equals 1, the entire string qualifies as the answer because each character in S appears at least once. These considerations are important when designing an efficient solution for this problem. To tackle the problem of finding the longest substring in which every character appears at least k times, we initially considered a brute force approach. The intuition here is straightforward: examine all possible substrings of the string S, count the frequency of each character, and check if every character within the substring meets the condition of appearing at least k times. If it does, we update the maximum length encountered so far. This method involves generating all substrings using nested loops and validating their characters' frequencies, which makes it computationally expensive. Specifically, generating substrings takes n squared time, and counting frequencies for each substring adds another n, resulting in a total complexity of n cubed. While conceptually simple, this approach is impractical for large input sizes due to its inefficiency. To improve efficiency, we explored the divide and conquer approach. The key insight here is that any character appearing fewer than k times in the entire string cannot be part of any valid substring. Using this observation, we divide the string into segments by splitting it at these invalid characters and then process each segment recursively. The steps involve identifying characters with frequencies below k, using them as delimiters to split the string, and finding the longest valid substring in each segment. Finally, we return the maximum length among all segments. In terms of complexity, this approach can be as efficient as n log n, when each split significantly reduces the string size. However, while it avoids the exhaustive checks of brute force, it still requires multiple scans if the splits are uneven or minimal. This method strikes a good balance between clarity and efficiency, making it a compelling choice for certain scenarios. Another method we considered is the sliding window approach, which uses a dynamic window to explore substrings while tracking character frequencies. The idea is to expand and contract the window to ensure that all characters within it meet the k condition. To optimize this further, we leverage the fact that there are at most 26 unique characters in the string. By iterating over all possible counts of unique characters, denoted as t, where 1 equals t equals 26, we dynamically adjust the window to maintain exactly t unique characters, ensuring their frequencies are at least k. This involves iterating through possible t values, using the sliding window to track valid substrings, and updating the maximum length accordingly. The complexity of this method is O(26*n), or simply O(n), since there are at most 26 iterations for the unique character count. While this approach is efficient and avoids recursion, it requires careful handling of edge cases, such as when k exceeds the frequency of any character. Ultimately, we chose the divide and conquer approach for its balance of simplicity, efficiency, and intuitive appeal. The core observation that characters with frequencies below k cannot contribute to any valid substring significantly reduces the problem size during recursion. By splitting the string at these invalid characters, we focus on processing only the potentially valid segments, avoiding unnecessary computations. Compared to brute force, this method is much faster, as it avoids redundant checks across all substrings. While the sliding window approach is asymptotically faster, the recursive nature of divide and conquer makes it easier to implement and debug in this specific problem. Additionally, it naturally handles edge cases, such as when no valid substrings exist or when k is larger than the length of s. That said, divide and conquer can be slower in cases where the splits result in minimal reduction, while sliding window may perform better for strings with uniformly distributed characters. Overall, divide and conquer provides a clean, efficient, and straightforward solution, making it the preferred strategy for this problem. In this problem, our goal is to find the longest substring of a given string where every character appears at least k times. To achieve this, we use a divide and conquer approach that breaks the problem into smaller parts and processes each part individually. First, consider the base case. If the length of the string is less than k, it's impossible for any substring to satisfy the condition, as no character can appear at least k times. In this scenario, the function simply returns 0. Next, we calculate the frequency of each character in the string using a frequency array or dictionary. This allows us to quickly identify which characters fail to meet the condition of appearing at least k times, which is a crucial step for splitting the problem into manageable parts. To divide the string, we traverse through its characters. If a character's frequency is less than k, it cannot be part of a valid substring. These characters serve as natural delimiters, splitting the string into smaller segments. For instance, if the input string is a and k is 3, the character b appears fewer than 3 times. This means we can split the string into AAA and CC. After splitting, we recursively apply the same algorithm to each segment to find the longest valid substring within them. Finally, we combine the results from all segments by returning the maximum length among them. If no characters have frequencies below k, the entire string is valid, and we return its length directly. This divide and conquer approach is particularly effective because it breaks the problem into independent subproblems based on invalid characters. Characters with frequencies less than k act as natural split points, allowing us to avoid unnecessary computations for substrings that cannot be valid. Unlike brute force methods that generate all possible substrings, this approach focuses only on segments that could potentially meet the condition, making it more efficient. Key data structures include a frequency count, implemented as a dictionary or array for constant time lookups, and a recursive stack to manage the state of each substring being processed. In terms of complexity, the worst-case time complexity is O(n squared), as the string could be split into n segments, each requiring an O(n) frequency count. The space complexity is O(n), determined by the depth of the recursive stack. Handling edge cases is essential in this algorithm. If the input string is empty, we simply return 0. When k is 1, any substring is valid, as every character appears at least once. If all characters in the string are unique, no substring can satisfy the condition unless k is 1, in which case the entire string is valid. On the other hand, if all characters in the string meet the frequency condition, the entire string is valid, and we return its length directly. To illustrate, consider the example where s is a and k is 3. First, we calculate the frequency of each character. A appears 3 times, while b and c each appear 2 times. Since b and c fail the condition, we split the string into AAA and CC. Processing AAA reveals it is valid with a length of 3, while CC has no valid substrings. The result is the maximum length, which is 3. After processing all segments and combining the results, the final output for this example is 3. This represents the length of the longest substring in which every character appears at least k times. By leveraging the divide and conquer strategy, we efficiently solve the problem while avoiding unnecessary computations, making the algorithm both effective and scalable. This implementation solves the problem using a divide and conquer approach. The function longest substring takes the string s and integer k as inputs and determines the length of the longest substring where every character appears at least k times. First, a helper function divide_n_conquer is defined to recursively explore subproblems. The base condition checks if the current substring length is less than k. If so, it immediately returns 0 because no substring can satisfy the condition. Next, the function calculates the frequency of each character in the substring using a dictionary. It iterates through the substring, and for any character that appears fewer than k times, it splits the problem into two parts, the substring to the left of the character and the substring to the right. The function is then called recursively on both parts, and the maximum result is returned. If all characters in the substring satisfy the frequency condition, at least k times, the function returns the length of the substring. This approach ensures an efficient solution by breaking the problem into smaller manageable parts. The runtime complexity is approximately n squared, in the worst case due to recursive calls and repeated frequency calculations. However, it works well for most practical input sizes. Here, we're implementing the solution using a divide and conquer approach in Java. We start with the main function, longest substring, which takes the input string s and the integer k. This function simply calls a helper method, divide and conquer, passing the entire string along with its starting and ending indices. The divide and conquer method is where the core logic resides. First, it checks if the length of the current substring is less than k. If it is, we can immediately return 0, as it's impossible for any character to appear at least k times within such a short substring. Next, we calculate the frequency of each character in the current substring using a hash map. This allows us to count how many times each character occurs between the start and end indices. After building this frequency map, we loop through the substring to find any character that appears fewer than k times. Such a character cannot be part of a valid solution, so we split the string at that position and recursively solve for both the left and right parts of the substring. Finally, if all characters in the current substring appear at least k times, we know the entire substring satisfies the condition. In this case, we return the length of the substring, which is simply end start. This divide and conquer approach ensures that we break down the problem into smaller parts whenever we encounter a character that doesn't meet the frequency requirement, while efficiently calculating the maximum length of a valid substring. By combining the results of the left and right splits, and considering the base cases, the algorithm ensures we find the longest substring where every character appears at least k times. To solve the problem of finding the longest substring where every character appears at least k times, we use a divide and conquer approach. Consider the input s equals ab and k equals 3. First, we call the function divide_n_conquer 0, 5, which represents the entire string. The base case checks if the length of the substring, calculated as end start, is greater than or equal to k. Since the length here is 5, we proceed. Next, we compute the frequency of each character in the substring, resulting in 3, b, 2. Now, we iterate through the substring to find invalid characters, those with frequencies less than k. We see that the first three characters, all up, are valid since their frequency is 3. However, at position 3, the character b has a frequency of 2, which is less than k. This means we need to split the string at this point, creating two subproblems, one for the left substring divide_n_conquer 0, 3, and one for the right substring divide_n_conquer 4, 5. For the left subproblem, divide_n_conquer 0, 3, we calculate the frequency of the characters in the substring, which is 3. Since all characters meet the condition of appearing at least k times, we return the length of the substring, which is end start equals 3. Now, moving to the right subproblem, divide_n_conquer 4, 5, the length of this substring is end start equals 1, which is less than k. Therefore, we immediately return 0 for this case. Finally, we combine the results of the two subproblems by taking the maximum of their outputs. The left subproblem returns 3, and the right subproblem returns 0, so the result is max, 3, 0, equals 3. This means the longest valid substring is of length 3, which corresponds to AAA. The final output for this example is 3. Now let's analyze another example with input s equals a BABC and k equals 2. We start by calling divide_n_conquer 0, 6 to process the entire string. The base case again confirms that the length of the substring, end start equals 6, is sufficient, so we proceed. We compute the frequency of each character, resulting in a 2, b, 3, c, 1. As we iterate through the substring, we find that the character at position 5, c, has a frequency of 1, which is less than k. This means we split the string at this point, creating two subproblems, divide_n_conquer 0, 5 for the left substring and divide_n_conquer 6, 6 for the right substring. Focusing on the left subproblem, divide_n_conquer 0, 5, we calculate the frequencies as a 2, b, 3. Here, all characters meet the condition of appearing at least k times, so we return the length of the substring, which is end start equals 5. Now, for the right subproblem, divide_n_conquer 6, 6, the length of the substring is end start equals 0, which is less than k. As a result, we return 0 immediately. To determine the overall result, we combine the outputs of the left and right subproblems by taking the maximum of the two. The left subproblem returned 5, and the right subproblem returned 0, so the result is max 5, 0 equals 5. This tells us that the longest valid substring is of length 5, which corresponds to a BAB. Therefore, the final output for this example is 5. Finally, let's consider the input s equals a b c d e d g h and k equals 2. We start with the initial call divide_n_conquer 0, 8 to process the entire string. The base case confirms that the length of the substring, end start equals 8, is sufficient, so we proceed. We calculate the frequency of each character in the substring, resulting in a 1, b1, c1, d1, e1, g1, h1. Here, all characters have frequencies less than k. This means no character in the string satisfies the condition, so we recursively split the string at every character. However, each of these recursive calls will result in substrings of length less than k, which means that all of them return 0. As no valid substrings exist, the result for this example is 0. The final output is 0, indicating that no substring meets the condition for this input. The time complexity of this solution primarily stems from its divide and conquer approach. To break it down, the algorithm first computes the frequency of characters within the current substring. This involves iterating through the substring, which takes n time, where n is the length of the substring being processed. Next, the algorithm scans through the substring again to identify characters with a frequency less than k. This second scan also takes n time. When such characters are found, the algorithm splits the substring into two smaller parts and recursively processes each half. These two steps, computing frequencies and splitting the substring, are repeated at each level of recursion, and this contributes to the overall time complexity. Now, let's analyze the recursive calls. In the worst-case scenario, the algorithm repeatedly splits the string into two smaller substrings. For example, if every character in the string appears fewer than k times, the splitting process continues until each substring has a length of 1. The recurrence relation for this process can be expressed as t, n, equals 2 * t, n/2, plus n, where t, n/2, represents the time for the two recursive calls and n, accounts for the frequency computation and splitting at each level. Using the master theorem, this resolves to a time complexity of n * log n in the worst case. On the other hand, in the best case scenario, all characters in the string already meet the frequency condition, so no splits are necessary. The algorithm simply computes the frequency once, resulting in a time complexity of n in this ideal case. Overall, the worst case time complexity is n * log n, while the best case is n. Let's now consider the space complexity of the algorithm. First, the frequency dictionary contributes to the space usage. This dictionary is used to store the frequency of characters in the current substring, and in the worst case, it will contain all unique characters. If the size of the character set is a, the dictionary requires a space. Additionally, the algorithm uses a recursive approach, which means there is a recursion stack. The maximum depth of this stack is determined by the number of recursive calls, which is O log n in the worst case due to the divide and conquer strategy. Combining these two factors, the overall space complexity is O a plus log n. However, for standard English alphabets, where a is constant, the space complexity simplifies to O log n. When comparing this divide and conquer solution to a naive, brute force approach, the efficiency becomes clear. A brute force method would involve checking every possible substring of the given string to see if all characters in that substring meet the k frequency condition. Since there are O n squared substrings and verifying each one takes O n time, the brute force solution has a time complexity of O n cubed. In contrast, the divide and conquer approach avoids redundant checks by leveraging frequency-based splitting and recursion, achieving a much more efficient worst-case time complexity of O n asterisk log n. To summarize, this approach achieves O n asterisk log n in the worst case and O n in the best case for time complexity, with a space complexity of O log n for constant-size character sets. This makes it far better suited for large inputs compared to the brute force alternative, thanks to its logarithmic recursion depth and efficient substring processing. When tackling this problem, there are several common pitfalls to be aware of. First, a frequent misunderstanding involves the at least k times condition. Some mistakenly count substrings where certain characters appear fewer than k times. For instance, in the string AAB with k equal to 3, one might incorrectly assume AAA is a valid substring, even though the B characters violate the condition. Remember, every character in the substring must appear at least k times for it to be valid. Next, edge cases are often overlooked. Scenarios like k being greater than the length of the string, k equal to 1, or strings where all characters are unique can lead to incorrect results or errors if not handled properly. For example, if k is 1, every substring becomes valid, which simplifies the problem significantly. Lastly, an inefficient brute force approach where all substrings are generated and checked can quickly become computationally expensive. With a time complexity of O n cubed, or worse, this method is impractical for larger strings, so optimizing is essential. Another common issue lies in frequency tracking. Using a single, global frequency map for the entire string can lead to incorrect results because it fails to account for the specific frequencies within the substring or window being analyzed. Instead, you need to maintain a frequency map that dynamically adjusts to reflect only the characters in the current range. Additionally, sliding window techniques are often overcomplicated. Some attempt to fix the window size or adjust both ends simultaneously without considering the actual character counts involved. A successful sliding window approach requires dynamic adjustments based on the number of distinct characters in the window, making it crucial to balance efficiency with the constraints of the problem. To approach this problem effectively, it helps to understand the core idea: for a substring to be valid, every character's frequency must meet or exceed k. This requirement often lends itself to two powerful strategies: divide and conquer and sliding window. Problems involving character counts or frequency constraints frequently rely on tools like hash maps, sliding windows, or recursive splitting, so recognizing these patterns during an interview can be incredibly helpful. Among the approaches, divide and conquer achieves a time complexity of O n log n, making it a strong choice for larger strings. However, sliding window methods can outperform it for smaller inputs when applicable. Lastly, always clarify input constraints and edge cases with your interviewer at the beginning. For example, you should confirm how to handle k values greater than the string length, empty strings, or cases where k equals 1 to avoid unnecessary confusion later. This problem connects closely with several others on LeetCode that focus on substring analysis and frequency constraints. For example, in LeetCode 3, longest substring without repeating characters, the emphasis is on applying sliding window and hash map techniques to ensure no character repeats. Similarly, LeetCode 424, longest repeating character replacement, relies on sliding window methods for frequency-based constraints. LeetCode 340, longest substring with at most k distinct characters, introduces the additional challenge of tracking distinct character counts, while LeetCode 159, longest substring with at most 2 distinct characters, highlights how edge cases like small k values can significantly impact your approach. Studying these problems can deepen your understanding of the patterns and techniques used in substring-focused challenges. Finally, let's explore some alternative approaches to solving this problem. The divide and conquer method works by recursively splitting the string at invalid characters, those that appear fewer than k times, and solving for each resulting segment. While its time complexity is n log n, the implementation is relatively straightforward, making it a good choice for understanding the problem. On the other hand, the sliding window approach uses two pointers to expand and contract a window, dynamically tracking character frequencies. With a time complexity of n*26, or n*d, where d is the alphabet size, this method is more efficient for smaller alphabets but requires careful implementation to handle dynamic adjustments. Lastly, there's brute force, which involves generating all substrings and checking each for the k condition. While this method is highly inefficient with a time complexity of n cubed, it can be useful for grasping the problem's fundamentals before moving to more advanced techniques. Great job! We've just covered an efficient approach to solving the problem longest substring with at least k repeating characters. Remember to practice similar problems to solidify your understanding of string manipulation and frequency analysis. Thanks for watching, and don't forget to like, share, and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!